Garrett.
Oh, he said the
Ooh, use that word. What's the relation between phase margin and pole Q?
Could you remind us what pole Q means specifically?
Yeah, the pole Q is the angle that the pole makes with the imaginary axis. Or it's determined by the angle that the pole makes with the imaginary axis.
Are you talking the Nyquist plot? The unit circle angle makes when the...
That's the phase margin. Okay, that's the phase margin. Nyquist plot, to my knowledge, there's no easy way to look at the relationship between the Nyquist plot and pole Q. Remember, the Nyquist plot was done in the 40s when we had a slide rule and a pencil and paper. And at that time, obtaining poles of a transfer function was, if it's much more than second order, was an onerous task. What's the relationship?
The homework says the square cosine of the phase margin and the square root of that over the sine of the phase.
We gave that equation on the board. Under what conditions? Under what conditions? Second order low pass. Under second order low pass, there's a closed form expression that relates the pole Q to the phase margin. If it's not second order low pass, what's the relationship? I don't know. We don't know. There is no general relationship if it's not second order low pass.
There's no analytical solution.
There is no analytical solution. Okay. So why do we use phase margin? We know a lot about what pole Q's tell us. Pole Q's tell us a lot about two important things. What do they tell us about? Particularly relevant when we're building feedback amplifiers, right?
They tell us about if we're going to have ringing.
Ringing in a step response or overshoot in a magnitude response, right? Pole Q's tell us some really important things about a feedback amplifier. What does phase margin tell us about a feedback amplifier? What?
Tell the same thing.
If it's second order low pass, it tells the same thing. If it's not second order low pass, you can do a partial fraction expansion. You can still get overshoot and ringing, right? So pole Q still give us overshoot and ringing information in the magnitude response. Phase margin. Not a whole bunch. So why do we use phase margin a lot when we're doing compensation?
Because
Why do we use phase margin a lot when we're doing compensation?
if only if we're interested in stability could we, but that's why I'm saying only. So in general, not much.
Yeah, I heard two people use that word, and again, the reason I don't like to use that word is if you're worried about that word, you've got a bad amplifier, right? So I try to avoid using the word because every time that word is used, it reinforces the thought that that word is what's important. That word is not what's important. What's important is magnitude characteristics, ringing characteristics, and so forth. That's what's important in an amplifier. Okay. So why do we use phase margin? Interesting about using phase margin, when you're done using phase margin to do compensation, you'll typically do a simulation, and you'll typically find the performance is not what you want, even though the phase margin might be what you want. And then you'll go and adjust your compensation capacitor to get the performance that you want. So maybe we can look at phase margin as being something that gives us a first approximation, but since it's not related to anything that we really want, it's kind of an artificial intermediate parameter, we wouldn't expect that it would necessarily give us the properties of what we would want. Today I'd like to talk about two-stage op-amps with left half plane poles. We talked about ones with right half plane poles before, and then I'll spend a little bit of time talking about breaking the loop. Recall from last time, actually this was the last time, this is the two-stage amplifier with Miller compensation. That Miller compensation capacitor was very clever. It was what Fluidgrad was able to come up with. The first time that an internally compensated op-amp was built, he called it the what? What did he name that op-amp, that project he was working on? 741. It was project number 741, so it's called the 741 op-amp. But his structure is slightly different than this, but the idea came from him at that time. It allowed us to dramatically reduce the size of the compensation capacitor if we put a capacitor from the drain node of the first stage to ground. That was so big in the past, before Fluidgrad's work, that we had to do that externally. You put it here, you dropped the size of the capacitor by about a factor of 100. That made it small enough you could put it on chip. But we saw that Miller effect didn't apply to high frequencies. The higher frequencies, it didn't quite look like a capacitor to ground any longer. And it actually contributed to 0 as a transfer function, and that 0 was in the right half plane. And we can see that it's kind of an undesirable characteristic, because that if we didn't have that 0 present, this term here, beta GMD, was absent. So this makes that S term small. If they make the S term smaller, we have to make a bigger compensation capacitor to get the term big enough so that we have the right pole locations. Okay, so this right half plane 0 has hurt us. It's made the compensation capacitor become bigger again to compensate for the reduction in the term because of this negative term here. And we had a closed form expression for the Q. We could analytically obtain the closed form expression for the pole Q. We could obtain and then we could solve for the compensation capacitor. When we're doing design, a lot of times the pole Q will be a constraint. We'll say we'd like a pole Q. Well, maybe you say we want a phase margin, and if it's a second order low pass, then that gets a pole Q. Got a little problem, because it's no longer second order low pass. So if we use that equation that relates the pole Q to the phase margin, we might not quite have the right Q here. But you can pick the Q, and now you can solve for C sub C to give a given pole Q when that right half plane 0 is present. Let me emphasize also that this analysis for the feedback amplifier that I've got here, it applies to this circuit, but it applies to much more than this circuit. What does it apply to? Any two-stage amplifier with a tail current bias first stage, a tail voltage bias second stage, and a current mirror connected counterpart circuit. So if I were to have a telescopic cascode structure here, for example, that's one of the problems in the homework assignment I posted this morning. How would this expression here on the upper right change? Garrett?
Just plug in the GMOs and You know, listen to the question carefully. How would the expression in the upper right change if I had a telescopic cascode stage here? It wouldn't. That was expression applied for any two-stage amplifier with Miller compensation. So now the question is, if I had a telescopic cascode first stage, how would I get the gain in terms of the small signal parameters of the devices in that telescopic cascode stage? Garrett, the answer is?
Just find the parameters of that stage and plug them in.
Right, just find GM0, GLO, GMD, and GOD, and plug those back into that expression on top. And is that important to observe this? Well, if you go and take the telescopic cascode amplifier and put in a small signal model, you're going to have a ton load of equations to solve to get this gain expression. And when you get done, you'll get the same thing. No, I didn't say that right. If you get done, you will get the same thing you get here by plugging in the values for those four two-port model parameters we have on top there. So this allows us to write down gain characteristics by inspection rather than going through a detailed analysis. Make sense? So this relationship down here, GMD equals GM1, GM0 equals GM5, and so forth, that's the relationship for this particular structure. If I have a telescopic cascode structure, which is a homework problem, these expressions here will change them. Yes?
Where is GOO and GOD in any of those expressions?
Okay, up here we need four terms. GMO, GMD,
And that's it.
GMD, GM out. Did I make a mistake on this expression? Oh. Garrett, help me out.
Smiling not.
Should there be one more term in the denominator? That includes the output conductance from M5 and M6.
No, this is right. This is right. I could have asked one other question. This is the gain with feedback. I didn't ask the question what the open loop gain was. The open loop gain for this two-stage op amp would have been, what did it look like? It would have been GM0, GMD over, and I guess the numerator is the same. It would have been S squared C sub C CL plus S C sub C, and I think it's just GM0 plus GOO GOD on this term right here. So the open loop gain would have been a different expression. We've written that down, but I don't have it here. So who asked that question? Yeah, right. So the reason it doesn't appear is the output conductances disappear in the feedback expression. They're in the open loop expression. We talked about the relationship between Nyquist plots and Bode plots or gain phase plots. We said that phase margin and gain margin were defined in the context of the Nyquist plots, but we can read them off quite easily off of the gain and phase margin plots. we need to emphasize that the gain margin or the phase margin, here I'm showing the phase margin, is strongly dependent upon beta. Different values of beta for most amplifiers will have different phase margins. And here was the relationship we showed last time. For a second order low pass open loop amplifier, the phase margin and the pole Qs are related by this expression, these expressions here. We observe that if we want a pole Q between 0.5 and 0.707, we want a phase margin between 65 and about 78 degrees. And this was a plot of the step response as a function of Z or as a function of Q. And we see that if Q is very high, we get peaking, this is a magnitude response, excuse me, we get peaking in the magnitude response. And this is the step response. And we see if Q is very high, we get ringing in the step response. So let's look at a design strategy now for this two-stage op-amp. The natural parameters are the widths and the lengths of all the transistors and the compensation capacitor C sub C and probably the tail current I tail and maybe the drain current in M6. So these would be the natural design parameters that we probably work with. If you're doing design and you get to the point where you have all these values here, you're almost ready to go to layout. I guess that you can convert this tail current and this drain current here and here to a WNL for these last two devices. So that's your goal, to come up with those natural parameters in a design. Total number of independent variables here are 13. And right now there's 13 degrees of freedom. If phase margin is considered to be a constraint, which it usually is, phase margin in the application you've got in mind for it, then we have 13 independent variables, one constraint, so there's really 12 degrees of freedom. Okay. Is that good or bad, that many degrees of freedom?
It's a good thing, but it's overwhelming.
It's a good way to look at it. We love to have extra degrees of freedom, but sometimes it becomes overwhelming to determine how to effectively use those degrees of freedom. But we saw in their device models, W and L appear as ratios, so realistically, the natural parameter domain is reduced to 8 parameters. With the phase margin constraint, we have 7 degrees of freedom. You can build an awful lot of different two-stage amplifiers with those 7 degrees of freedom. And they can all work. If you look at the performance parameters in op-amp, I've listed some of the things that we're interested in. Signal swings and slew rates and the gain and noise levels, offset, a lot of things we're interested in. I happen to list 17 parameters here. Almost every design, you probably at least are going to look at what most of these parameters are. So we have 17 performance parameters and 7 degrees of freedom. So we're really highly over-constrained. Even though we have a lot of degrees of freedom, even though we have 7 degrees of freedom, we have more performance parameters than degrees of freedom. If you looked at the two-stage amplifier in terms of the two-port model parameters, which is what we use to analyze the circuit, we see in the small signal two-port parameter domain, we have GOO, GOD, GMO, and GMD. For the two-port model, we have the compensation capacitor, and then we have the output conductances of the transistors as well. So it doesn't take long to end up with having expressions that involve lots of different parameters. Let's look at the signal swing in this two-stage op-amp. these are the conditions that are necessary to keep all of the transistors in the saturation region. And it's just the expression that says the gate source voltage has to be bigger than the threshold voltage, and the VDS has to be bigger than VGS minus VT. So these are the locuses that define the regions of operation for the device, where VIC is the common input, and Vout is the output voltage of the device. So if you look at the signal swing equations that are governed by these inequalities, there are functions of excess bias voltages and I have tail current. It doesn't show explicitly in here. So if I plot those inequalities, you can see all those inequalities are actually straight lines. What's the difference between a line and a straight line? All those inequalities are lines, and they're either horizontal lines or vertical lines. And I put arrows here to show each of these inequalities. So I've listed the inequalities, and then I listed the arrow to show which direction it's going. So if you look at what you have to do to keep all the device in saturation, you have to lie in the region that's the intersection of all these inequalities. Not too bad. In this case, that intersection region is a rectangular region. We saw earlier, we had a single stage amplifier, we had a trapezoidal region. Here we have a rectangular region. That's pretty nice. So here's the regions of operation of the device, the common mode input range and the output range. Okay. So it looks like as long as your supply voltage is not too small, you can have a fairly large common mode input range, and you can have a fairly large output range. But notice that the output range on this structure doesn't get up to VDD. It doesn't go out down to VSS. So we're bounded away from the upper and lower rails on this architecture. And the common mode input range is bounded away from VSS, and it's bounded away from VDD. Okay. So I'm going to give an augmented set of design parameters because we see these, the gain characteristics were in terms of these two-port parameters. We see the signal swing characteristics are in terms of some excess biases. We see that the two-port parameters are a function of parameters of the transistors themselves. So we've got a lot of parameters that appear in different expressions. And these parameters are highly interrelated to each other. So when we're trying to do design, we'll have equations that involve different subsets of these parameters, and one relates to the other. Make sense? Common expression for the performance parameters, the gain, the DC open loop gain is GMD GMO over GO GOD. GB is GMD over C sub C. Slew rate is I tail over C sub C. And we have these signal swing expressions as well. If I look at these expressions, I'm going to take 4 of them. The DC gain, the gain bandwidth product, the slew rate, and GMD. GMD is one of the parameters that appears in that two-port model. And I see IT affects the slew rate here. It affects GMD. It affects the gain. It affects the gain bandwidth product. Is that good or bad? It's bad. It affects everything. You change IT, and some stuff goes up, but some stuff goes down. Some stuff goes the way you want it to go. Some stuff goes the way you don't want it to go. So if you ask the question, how does IT affect the performance of this amplifier by itself? It looks like it's really hard to say. Here are the natural parameters we like to work with in the design, the WRL ratios, the tail current. And here I'm going to define theta to be the split of the power between the first stage and the second stage. So it's ID6Q, which is the current in the second stage, divided by the total current. Or it's the power in the second stage divided by the total power. So we have 7 degrees of freedom, and one constraint, that's the phase margin constraint or the pole Q constraint. So I'm showing the 7 degrees of freedom here in this set. And let's look at some of the performance parameters in terms of this parameter, these natural parameter set parameters. Now we've already done this before for a single stage op amp, right? Now we're going to do the same thing for a 2-stage op amp. Do you think things will get easier or more difficult? Probably get more difficult. Okay? So if I express A0 in terms of this parameters in the set, which you might be exploring, here's what A0 looks like.
Beautiful.
What? Beautiful. It's beautiful because you've got the expression. It's horrible if you got to work with it. Right? Well, if only one expression was bad, it wouldn't be too troublesome. Here's GB. Got square roots here, a couple of different parameters. Here's C sub C. It's kind of a mess too, isn't it? Here's V and min in terms of those parameters. You got the sums of the ratios of square roots. Is that good or bad? I got tired of writing things down. That was just V and min. There are 4 boundaries to the signal swing. So we've got 3 more equations that look something like this. So the expressions for the signal swings are particularly complicated. In fact, even the most elementary performance parameters, gain bandwidth product, signal swings, require very complicated expressions when we use the natural parameter domain. There's strong simultaneous dependence on multiple natural design parameters. We saw I-tail affected almost everything in the small signal performance characteristics. So the interdependence and the notational complexity really obscures insight into how it performs, and it obscures insight into optimization. So let me go back and identify another parameter domain. Keep in mind, you can define any parameter domain you want. The excess biases work pretty well for us on a single stage op amp. So let's try the excess biases, the power, and the power split between the first and second stage. How many parameters do I need in this alternate parameter domain? I happen to have 7. The reason I picked 7 is what? Garrett. Why do I pick 7?
7.
Yeah, 7 in your natural.
Yeah. And why did I have 7 in the natural? There were more than that to start with. Why did I have 7 in the natural?
Do you assume the phase margin constraint?
I assume the phase margin constraint. 7 is the number of degrees of freedom. So if we're going to explore design space, the number of parameters you want to work with equals the number of degrees of freedom you have in your design. So I don't list C sub C in this list, since it's listed as a constraint. I eventually want to make a mapping between these practical parameters and these natural parameters. So let me just go ahead and show that that mapping is pretty straightforward. The tail current is equal, that's the current in the first stage, is equal to P over VDD, that's the total current, times 1 minus theta. So I know what the tail current is. So each of the currents in all the transistors are either I-tail, that's the lower transistor, or I-tail over 2, that's the transistors on the left and the right side, or theta P over VDD, that's the current in the 2 on the right. So we know the currents for all the transistors. And then the WRL values are all given by the expression 2 times the current over mu Cox V excess bias. So it's very easy to go from the practical parameters to the natural parameters. Okay. So let's look at some of the let's look at the performance parameters now in terms of the practical parameters. The DC gain, 4 over lambda n plus lambda p squared times V excess bias 1 times V excess bias 5. Simple expression involves 2 parameters. GB, well, we derived this expression earlier. It was P, you can express it as P times 1 minus theta over VDD V excess bias 1 times C sub C. But C sub C was, we had a closed form expression for C sub C. And if you do that, this is the expression for GB. GB is a little bit of a mess here. But is it as bad as those expressions that we had for signal swing and so forth earlier when we used the natural parameter domains? No, it's still not too bad. And it involves 4 parameters, so it's a little bit tedious in that sense. The slew rate expression is very similar to the GB expression. Compensation capacitor expression is given here as well. So those are a little bit tedious expressions, but the signal swing expressions are really, really nice to work with. So let's look at a design example. I'm going to assume the following system parameters: VDD of 3.3 volts and CL of 1 puff. I'm going to use a 0.35 micron process, and I'm going to eventually simulate this at typical 55 degrees centigrade and a 3.3 volt supply. Given specifications, I'm going to assume I want an op amp that's got a gain of 66 dBs, a gain bandwidth of 5 megahertz, V out min of 0.25, V out max of 3.1, V in min of 1.1, and V in max of 3. I'm going to assume that I want to limit the power to 170 microwatts, and I'm designing it for a feedback factor of beta equal 1. I'm going to neglect loading the beta network right now. I'm assuming these values for the threshold voltages on the devices. So what I have is 7 constraints and 7 degrees of freedom. I've chosen to set the number of constraints equal to the number of degrees of freedom I have in my design. So let's look through a design procedure. First thing I'm going to do is choose a channel length. All the transistors, I'm going to assume, have the same length. And now I have expressions for V in max, V out max, and V out min in terms of excess bias voltage. Now, if I want to satisfy V out min requirement, that fixes V excess bias 6. So I can mark it off. And if I have a V out max requirement, that sets V excess bias 5. So I can mark it off. And if I have a V in max requirement, that fixes V excess bias 3. So I can mark that off. So I'm left then with 4 unknowns after I satisfy the signal swing requirements. The DC gain was given by this expression. Now V excess bias 5 was fixed by a signal swing requirement. If the gain is fixed, that forces V excess bias 1. So now I can mark V excess bias 1. Now I've got 1, 2, 3 things left. V and min, I didn't include it up there. I chose to do it in this sequence for reasons that should be apparent. V and min is V excess bias 1 plus V excess bias 7 plus VT. Well, V excess bias 1 has now been determined. So I can get V excess bias 7 from this equation. And I can mark it off the list. Is everybody with me? So I've looked at that set of equations, And I've tried to satisfy them in a sequence that will allow me to uniquely identify a design procedure. And you should be able to do this with most designs. So at this point in time, how many unknowns do I have left? Power and theta. So I'm going to choose P to satisfy the power constraint. And that just leaves theta left. So now I've got a situation where I still need to satisfy the GB requirement. So GB was P times 1 minus theta over B to D VXS bias 1 sub C sub C. And everything's, and C sub C is given by this expression, so I can plug that back in there. And it's kind of a complicated expression, but I can solve it, either iterate to solve it or solve it with a computer to get theta. And I'm done. Then I calculate all transistor sizes. We saw how to do that earlier. And then implement the structure, simulate, and make modifications if necessary. Now, we don't expect the circuit to work exactly like we modeled here. If this was really how the device operates, we're done. But we might miss some diffusion capacitances or something else that are not included. So we simulate it. And if we're lucky, we won't be too far off. And then we can go back in and you know, if the gain's not high enough, we know how to increase the gain, make the excess bias one a little bit smaller. If the signal swing's not quite enough, we can go tweak an excess bias. And does that make sense? And so that's usually pretty easy to break these into spec. So it may be necessary or preferable to make some constraints. I wouldn't even comment on that. Some of them might choose to make it inequality rather than equality. I may have chosen to make the gain a little bit bigger than I needed. So if you lose a little bit of gain because of other effects, maybe instead of starting out with 66 dBs, maybe we want to start out with 72 dBs. And then if we get 69, then we say, well, that's good enough. It's a little bit more than I needed. So if I try to satisfy these inequalities exactly, then I'll probably be a little bit under-designed. If I set slightly tighter specs and design a lot of times, I will get acceptable performance. Design results. I set, I guess in the design, I set all the L's of 2 microns. So here's what the design procedure I just went through gives me for this design. When I put in the value of 66 dBs, the 5 megahertz, and so forth. And I simulated the structure after I designed it in SPICE. And I find that I have 5.2 megahertz GB. What was I trying to get? 5. I see a DC gain, A0, of 65 dBs. What was I trying to get? 66. I'm a dB off on my gain. My power is right on. My phase margin a little bit soft. I find something like this is really useful. I like to use a spreadsheet to guide my design. I've seen myself try to use a pencil and paper, and after 2 days, I've got papers all over the place with a whole bunch of different designs. And at the end of a day and a half, I was close before, and I can't get this GB back. Now, where was that at? And so I go try to find out where I was. Have you ever done that? Oh, yeah. So what I try to do is have one section of the spreadsheet set up with the design parameters. In this case, there's 7. If I do a design, I enter the values of that design that I'm working on. And then I calculate, I have equations for the performance parameters. So then I have equations behind each of these cells in the spreadsheet, and that pops out exactly what's going on here. And the input range, there also are design parameters. And then the device sizes, we have closed form expression that allows us to calculate these. So if I am not in a situation where I can break it sequentially to solve the equations, right now I picked this example so that I could go through, and the only equation that was complicated to solve was that last one, right? But it could be the case that there's a couple of equations that are interrelated here, so it'd be a pain to maybe solve those. So what I can do is I can iterate then on the spreadsheet, and I might not know what VXS bias 1 and VX bias 3 should be, so I can put in different values of VXS bias 1 and VXS bias 3, and I can immediately then see what the effects are going to be on the performance of that system. So what do I have here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 15 op-amp designs here. And as I'm going through the design procedure, I try to decide which parameters I might need to change if I don't have closed form analytical expression for everything. How long does it take to put together a spreadsheet like this?
Not too long. Setup time. And then
What?
you get a little bit of setup time, but then you can.
That's right. You got some setup time to do it, but we have closed form analytical expressions for everything in that spreadsheet. Oh boy, once you got that done, forget about that pencil and paper and all those. And if you do the pencil and paper route, what happens? The gain wasn't right. So I changed the parameter to make the gain better. Now, what happened to slew rate? You go calculate that. What happened to the GB? Got to go calculate that again. What happened to the signal swing? Got to go calculate. Oh, rat, something went wrong. Yeah, you got the picture. So, in summary, determination of design space and the degrees of freedom is often useful for understanding the design problem. Try to make it look systematic. Analytic expressions for key performance parameters give a lot of insight into the design potential. The natural design parameters are often not the most useful. Well, I think we saw an example in this case. If I would have tried to give a procedure for doing the design based upon the natural parameters, it would have been a pain. And these concepts apply to most structures. Let's talk about power distribution between the stages. Somebody asked this question earlier. How would we split the power between the first stage and the second stage? Who asked that question? Somebody in here asked that question. Don't be embarrassed. It was a good question. What? Maybe I'm imagining things. So, we would often like to minimize the power for a given GB requirement. So we'd like to allocate the parameter theta appropriately between the two stages. So I'm going to consider now the structure that doesn't have the right half plane 0. I'm going to just assume a compensation capacitor C sub C here. We derived expressions for the gain and the gain bandwidth product and so forth of the structure. I'm going to assume that the pole spread is 3 beta A naught P1. And the reason I used that was we had a nice way to decide how to compensate the structure. We said we wanted to have the pole spread between 2 and 4 beta times the gain bandwidth product. So I can write an expression for the gain bandwidth product in terms of theta, the power, and beta, and CL. And if I write it in this form, I'm about out of time, so I'm not skipping anything that's difficult. There's nothing more complicated than what I've got written on the slide here. If I've got GB written in this form, I see GB is now a function of the parameter theta. And if I want to optimize GB, maximize GB for a given power, what does this tell me I have to do? Maximize theta. And theta is the fraction of the power that appears in the second stage. So that tells me to have the most efficient power amplifier here, I want to push almost all the power in the second stage. Make sense? Thus, for a given GB, we want to make theta close to 1. Keep the devices out of weak inversion on the first stage. So this optimum power split was based upon dominant pole compensation on the first stage. The results might be a little bit different if we have the right half plane zero structure, but the approach is basically the same. We saw that right half plane pole caused a problem. It made C sub C get bigger. Question is, can anything be done about this problem? I've got a break here. So I'll show what's going on here, and then we'll pick it up tomorrow evening. If you don't have that right half plane zero present, and that was the approximate expression we got when we looked at the poles on the nodes, you would see that the all-pole amplifier would come down like this. That right half plane zero causes the gain to not drop as fast. It slows down the dropping of the gain. If you look at the phase, that right half plane zero makes the phase drop faster. When you have the phase dropping faster, you tend to move the poles towards the imaginary axis, or you tend to degrade the phase margin. So we see that right half plane zero added additional phase shift, which had to be offset by increasing that compensation capacitor a lot to compensate for it. So that's what it does to us. Tomorrow evening we'll look at what we can do to remove those problems, to move that pole from the right half plane back in the left half plane. Any questions? That's all for today, thanks. For those that didn't notice, the homework assignment has been posted. Also, the session tomorrow night, the marathon session tomorrow night, is in room 1016, Coover.
When's the homework due?
I got set up a week from today.
What did you say?